Hello and welcome everyone to another Applied Flow Technology webinar. My name is Nick Vastine. I'm a Business Applications Engineer here with AFT, and today we're going to be going through an introduction to our product AFT xStream. This will be an introductory webinar, so if you have very limited experience with our software or with xStream, you should be in the right place. So first we'll do a brief introduction overviewing some of the assumptions and applications of AFT xStream. And then we'll take a look at our first model in examining a tank blowdown event. So AFT xStream is our compressible transient solver, which means that it's compressing or it's modeling both compressibility effects while tracking things like pressure waves and dramatic changes in flow rate or flow velocity as it permeates throughout a piping system. So we'll go through kind of the approach for modeling and analysis. And again, if you have experience in AFT software already, especially in AFT Impulse, we'll see how all of those skills translate. A lot of the webinar is going to be dedicated to discussing the complexities of compressible transients and how AFT xStream accounts for all of these different effects. So we'll look at, again, compressible flow, the compressible part of compressible transients, pipe sectioning, which captures those transient effects, and how we have to modify that solution to account for kind of the idiosyncrasies or the more complex aspects of compressible flow. And then finally, how do we initialize our solution? What is going on in the back end for the solver? So a common theme that we'll talk about is not only do you have to understand the hydraulics of a compressible transient event, it's also important to understand how the solver in the back end works. So that way you can create a more staged approach to running your models. You know how to get the most accuracy out of the solver. And also, again, how do you interpret those results and make sure that they're reasonable, especially as you're making those engineering decisions. So we'll make some other modeling recommendations, just some kind of tips and tricks, especially if you are getting into AFT xStream. We'll talk a bit more in depth about our PFA or pulsation frequency analysis module. And then finally, we'll touch on some other resources because AFT xStream is generally a more intensive product. We have quite a few different resources you can take advantage of to refine your skills or to kind of call out for help as you get into your model and get into your system. So to give you some context, first I want to tell you about where AFT xStream fits into our product offerings. So AFT specializes in all piping systems, whether that be liquid flow or gaseous or steam flow, what we consider kind of compressible versus incompressible. So on the steady state side, or on the liquid side, I should say, AFT Fathom is our most common application. Again, looking at things like cooling water systems or other utility systems where we're sizing pumps for efficiency and reliability. AFT Impulse, this is our quote unquote rapid transient solver. It can model things like Waterhammer effects or check valve slam. And the way it does that is through pipe sectioning. And so we'll talk about AFT Impulse in a bit more detail and how we can take this liquid specific product based on the method of characteristics, something very established in the Waterhammer analysis world, and we'll apply it to AFT xStream, transitioning it to that compressible flow. And then similarly for liquid flow, we also have that pulsation frequency analysis module. On the gas and steam side, we'll also talk briefly about AFT Aero. AFT Aero is our steady state compressible flow tool. So if you're looking at steam distributions or natural gas systems or air systems, where the compressibility of the fluid will vary quite dramatically. You want to model that in AFT Aero because it's going to be a much more complex solver than AFT Fathom to, again, calculate all those different compressible complexities. So if we take AFT Aero and we take all of the complexity of compressible flow, we take AFT Impulse, all of the complexity of rapid transient flow, and we combine them, we get AFT xStream. So again, as I mentioned, the majority of the webinar will kind of dive into what's going on in the back end after we go through a kind of simple example. I would say xStream can be not necessarily misleading, but it can be very approachable, so much so that it's really up to the user to better understand what kind of assumptions are they making in building a model that may not be kind of strict checks with the user. but things that naturally occur as the user is building the model, making sure that they understand the input so that the output, the results that you're going to make those final engineering decisions on are going to be as accurate as possible. So let's take a look at AFT Extreme. So some of the engineering assumptions. Again, we're going to be modeling what we call rapid transients. That means effectively capturing how pressure and flow can change throughout a piping system during a transient event. So here on the left, we have a turbine trip example where we have two turbines that are running, and then we simultaneously trip them, and we want to see how this bypass valve performs. So whether we need to open this faster, open this slower, if we have any pipe forces concerns, those types of things that we could model, because as these turbines trip, the flow rate demand immediately goes down. If we're still supplying flow, you can see things like line pack. If this is missized and this has too high pressure, maybe you develop sonic choking through this line. And then also if you have, in this case, high pressure steam, you can also consider heat transfer effects along the piping as well. So some common applications, again, as long as it is a compressible fluid and you're concerned about that quote unquote rapid transient modeling, quite a few different things fall into that category. So for example, if you're sizing a relief valve, let's say this is a relief valve that responds to an overpressure event when these two turbines trip, you could size and make sure that you're going to get adequate flow through that relief valve. Rapid blowdown and charging. Today we'll be looking at a blowdown example, but you can have essentially fixed volumes and determine, using thermodynamics, if I'm losing this amount of mass, how much is coming from pressure, how is the temperature in the tank dropping, and that's something that we'll look at today. Ensuring that we maintain conditions, especially for very expensive turbines or very expensive compressors, they have a very limited operating window. So if we have a disruption event, let's say only one of the turbines trips and not the second one, how do we ensure we have adequate flow to the second turbine throughout that entire transient event? Unbalanced forces, as I mentioned, as pressure waves transmit through the system, we'll look at how the forces or the unbalanced forces on the piping will be affected. So we'll touch on the theory of that quite a bit in the lecture as well. Flow delivery time, how long does it take to develop flow to a consumer? And then pulsation mitigation, again, that pulsation frequency analysis module. If we have a reciprocating compressor or other kind of oscillatory component, how can we include a tank that will dampen those effects so that we don't get that oscillation throughout the entire system? And again, that's a concern because of vibration and pulsation. It takes very little energy operating at a improper frequency, we'll say, to resonate with the system. Again, it's like pushing a swing, but you're pushing it at the perfect frequency over and over, constantly adding energy, and that leads to a very short time to failure. Common systems, again, anything that's going to have a compressible fluid. What we've found through kind of initial discovery, as some people have been purchasing AFT Extreme, is especially on the turbine side in the power industry, steam systems as well. But again, I wouldn't limit it to these systems as long as you have a compressible fluid and you're invested in these kind of rapid transient events. Odds are you can look to AFT Extreme to try to model them. So here, instead of we were looking previously at the workspace, showing all of our different connections. This is a graph showing how pressure is going to change over time. And again, we're considering events that are happening on the order of milliseconds or even less in some cases. So a very gradual tank blowdown, something that might happen over the course of hours, that isn't necessarily suitable for AFT Extreme. I would instead point you to AFT Aero XTS, which similarly captures transient effects, but not these rapid transients as they transmit through the system. And then also we can look at force analysis. As I mentioned, this unbalanced forces, where because of compressible flow, in essence, you don't have the same fixed pressure wave as you might see in liquid flow. What happens is the pressure wave actually steepens, more and more of it can fit inside of a pipe, and you'll see your forces actually increase over time. So we have a great technical paper that covers this in a lot more detail than we will here. But if you're in the pipe stress analysis or you're sizing supports for piping, and you're basing it off of transient forces, it's important to consider, the compressible flow doesn't behave the same way as a liquid. You can see this more dramatic forces over time. So one thing that I'll note is AFT software is designed around a common interface. So as we'll see, if you have experience in Fathom, Aero, or Impulse, you should be able to jump into xStream with some relative confidence. However, if you aren't familiar with the basics of our software, due to the nature of the product, we won't go into kind of the same detail as I would introducing a product like AFT Aero. So if you're considering AFT xStream and you're looking for a more in-depth or more detailed introduction, definitely look into this webinar, and it'll go into the workspace, output, all of the reporting features in a lot more detail, whereas this webinar is going to focus more on the specialties and back end of AFT xStream. So if you're watching a recording, put a bookmark, pause the video, go take a look at AFT Aero, come on back, and then we can talk about the transient effects. So let's jump into the software. So now we're in AFT xStream, and we're working in AFT xStream 3, which is a, at the time of this video, upcoming version, but should be the currently released version as you're watching a recording, especially if you're in the future. So here we have our tank blowdown system. So we're looking at a supply tank, where if we go into the tank, we can take a look at its conditions. It's a finite tank instead of an infinite tank. So we're going to capture how is pressure going to decay, how is temperature going to decay, and typically you expect a kind of exponential decay when things are decreasing with your driving force. We can specify the finite tank volume. So here it's 8.5 cubic meters. We know the initial conditions. We could calculate it from steady state. Let's say we have an intermediate tank within our piping system. You can say, oh, it's going to operate at this pressure and temperature based on the inlet flow rates. And then from there, it can act as effectively a dampener to any other transient events coming into or out of it. Or you could model overpressure if it can't release pressure more than it has coming in. Again, is it going to pop off a safety valve or a relief valve? And the thermodynamic process, here we're looking at adiabatic. You can also fix the temperature. Again, maybe if you're looking at much longer transient events, that might be reasonable. Adiabatic might be more representative because the event happens so quickly, there might be limited heat transfer between the tank and the environment. You can also specify a known heat and volume versus time. Again, how could you heat or cool the tank over time to capture those thermodynamic, those compressibility effects? So that's how our tank is defined, and we're going to be going through two pieces of piping. We'll come back to the piping. If we look at our assigned pressure, we're discharging to 1 bar at 21.1 degrees Celsius. So let's look at the piping real quickly, and then we'll take a look at our valve. So the piping connections here, we're looking at 2-inch pipe, and it's 457 meters, a very specific meter length. And if we take a look at this heat transfer tab, here we can see kind of one distinction from Aero is that we're looking at it adiabatic at the internal surface of the pipe. So by default, we're not considering heat transfer effects through the piping or through any insulation, through convective heat transfer, of air or water or something transmitting over the insulation. Here it's isolated adiabatic at the internal surface. So it's a much more kind of theoretical consideration. It's perfectly adiabatic. Any heat introduced into the system through something like a compression wave is going to be trapped within the piping. So we'll take a look at how that can impact our results as well. And then we have another scenario where we'll look at adding convective heat transfer also. And if we take a look at pipe 1, similarly defined here now 6.1 meters instead of 472. So while it's visually represented, this pipe looks about twice as long as this pipe. This pipe is dramatically longer than pipe 1. So if you're familiar with AFT Aero, again, all of the input will be consistent. If you have an AFT Aero model, you can also import that into xStream. Alternatively, if you have a piping layout from a PCF file, Caesar2 neutral file, GIS shapefile, or EPANet file, you can also import those layouts. That should give you a better starting point for what are my pipe lengths, what are my pipe diameters, you can add some boundary conditions, some valves, and you're off and running on your transient analysis. So now let's take a look at the valve. And here we're going to be looking at a user-specified loss of a KV of 52. If we wanted to account for valve characteristics, we could add things like our open percent. How does our KV change with open percent? Our flow area, our XT, which is specific to compressible flow, determining essentially a sonic choking ratio. Here in our optional tab, the valve is initially closed. Again, we're modeling a tank blowdown event, so we're maintaining back pressure. And in our transient event, we go from completely closed, and in a fraction of a second, we go to completely open. And we maintain that completely open throughout the length of the transient, in this case, a transient duration of 240 seconds. So the system is going to run for 240 seconds. We want to examine kind of the corresponding results. Another thing that I'll note is all of my results have been run, so everything marked here in blue is already run. We're doing that for the sake of time. As I've talked about, the kind of complexities of AFT xStream Solver warrants a longer runtime. So for your interest and for my interest, we will avoid running the models in the webinar. If you're curious, this system took about 2 minutes to run and to generate our results. I'll throw in some other kind of small tips and tricks of how you can improve that runtime, especially on initial design conditions. So we've reviewed our workspace. Let's actually take a look at our quote unquote initial steady state. So as if we are just opening this valve first. And we'll be able to touch on some of the compressibility effects of AFT xStream and kind of create a starting point for what we expect the transient to model. So here we have those same conditions, but now if I go to this MOC transient button, here instead of modeling the transient event, instead of modeling those 240 seconds of simulation, I've just checked this AFT arrow steady. So the whole solver is kind of initialized on AFT arrow results. Again, it's a relatively robust compressible solver, so we can use that for our transient analysis as well. So here we're just going to do, again, quote unquote, an initial steady state, as if this valve has just opened and we're not modeling, you know, the immediate decrease in pressure and temperature in the supply tank. Essentially time step 1 when we first open this valve. And again, we just have our steady state results. Model data, again, not to go too in depth, this is where you can review your input. And here with our output, we can see here we have our AFT arrow steady results. We can see our velocity coming in and out. And the first thing with compressible flow is now our density is no longer fixed. So we see that decrease in density or increase in velocity. And that's even more dramatic in pipe 2. If we take a look at our Mach number, or how close are we to sonic choking, we can see that we get very close to sonic choking at the endpoint of pipe 2 as well. And if we check the sonic choking tab, we can see it's actually does exist at junction J3, which tells us when we start our transient event, we want to take a look at sonic choking, or, you know, we're going to run into a speed limit when we start our transient analysis. Let's take a look quickly at graph results, and we'll take a look at our steady state graph. And here we can see, again, those compressibility effects in a bit more detail. So here, if we look at our pressure, we can see our pressure decrease along the length of the pipe, and we see it's not a linear decrease. We see it actually gets more steep towards the end. And the reason it becomes more steep is if we look at our density decreases pretty linearly, and it starts to drop off more dramatically towards the end. As that density drops off, our velocity increases. As our velocity increases faster and faster, we get more and more pressure loss, lower and lower density, higher and higher velocity, until we achieve that sonic choking event or condition at the end of the pipe. So here, this graph, we're looking at a profile graph. So how are the parameters changing along the length of the pipe? So how is it changing from our supply tank through our valve through our pipe 2? And again, we see that steep drop off in temperature and velocity. So the way we capture these compressibility effects, this is where we perform a lot more calculations. to get finer and finer resolution. So as temperature changes dramatically, as our pressure changes dramatically, we're able to recalculate those properties, ensuring that we're capturing this dramatic sonic choking and dramatic change in fluid properties as best as we can. So that's what it looks like on the steady state side. And again, this will be our expectation when we start looking at our transient analysis. So now let's take a look. Let's go back to our workspace. And here we're going to now look at a feature called workspace layers, where, for example, we can look at what's our maximum velocity. So layers control style of our piping. So if we show both of our pipes, and let's say we wanted to make them thicker, we can do that within a layer. We can change their color. But what I want to show here is adding things like our pipe parameters so that I can show this result on the workspace itself. So if we wanted to look at what's our maximum velocity, here it's limiting me because we're not looking at transient, I believe. But if we look at the outlet velocity, which should be the fastest throughout the pipe if we're not cooling it down, we see 356 meters per second, 27 meters per second. And you can also add other parameters like, let's say, our pressure loss. So that way, at a glance, imagine a much larger system. I don't have to check my output, come back to my workspace. I can very quickly spot check all of these different parameters. We'll come back to workspace layers when we start doing our transient analysis. For now, I can hide this layer, and I show that all of my specifications, my colors, my different parameters I'm showing, they become hidden, but they're not gone forever. I can re-enable them. So if I have a more structured analysis, I can enable them and disable them as I need. So we'll disable it for now. And now that we've reviewed our steady state, let's go ahead and model our transient event. So we'll go back to our base scenario where we have our supply tank. We have our valve, which is going to open in a fraction of a second, 0.1 seconds. And then we're venting to, I believe, atmospheric conditions, 1 bar. And we've gone ahead and run our model. And if we take a look at our output, it looks a little different from our steady state case. Here we can still see those steady results. In this case, because the valve is closed, there's no mass flow, therefore there's no velocity. Again, our quote unquote initial steady state was that first time step where the valve is open. Obviously, we can't model that in a transient sense. We have to back close the tank because otherwise it would start draining essentially immediately. So we can look at the pipes. If we wanted to look at how the pipes were sectioned, we can see those splits. And if we look at the transient output, so this would show how our temperatures and our pressures are changing, our velocities are changing over time. However, this is obviously a tedious way of approaching it. So we'll look at a graph here in a moment to show how the transient permits through the system. Excuse me. We can also look at the transient maximum and minimum conditions. So if you're looking for things like what temperature do I reach during the transient event, this tells you at a glance it's nearly 920 degrees Celsius. We'll talk about why this maximum temperature is important a little later in the webinar. And if we look at, let's say, the maximum pressure as well, we can see it maintains at 45 bar, which is our pressure of our tank, which makes sense. We're not adding any higher pressure sources within the system. It starts at very high pressure in our supply tank, and we see that gradual decay as the tank discharges its contents. And then also heat transfer. So here, again, because we're looking purely adiabatic, again, adiabatic at the inner surface, we're only looking at the temperature of the fluid. And if we wanted to, we can also look at a result, which further shows, hey, we have our bulk fluid, our inner wall, the conductance through the wall, and if we had insulation or something of that nature. So if we look at our event messages, We can see here the valve sonically chokes immediately. So when we open the valve, we have all of that back pressure and it's going through a very tiny area. So it sonically chokes and it stops sonically choking as that pressure wave transmits through the system until we become sonically choked at our discharge point, and then it loses sonic choking at 130 seconds. So we'll keep an eye on these times and we'll see if we can pick them out as we start looking at our graph results. Again, if you're familiar with our software, you can copy and paste all this information as well, though in most cases, what I'm going to recommend and what we typically recommend as a company is investing more so in these graph results to visualize your transient event. So we'll go back to graph results where we looked at that steady state graph before. And here I have a pre-made profile animation where we can look at pressure, temperature, static, velocity, or density component. And so to begin, let me remove some of these parameters and we will regenerate our graph. So now we're looking first only at pressure. And we're looking at, again, length along the piping system, where we have our high tank pressure. We go through our valve, which is preventing the high pressure to low pressure. We're preventing any flow. And then we're fixed at that 1 bar of pressure because of our discharge condition. So we can time step by time step. So here, if you look at this time up here, as we open the valve, we see the pressure decrease along the line. So our tank is maintaining its pressure so far. We're seeing an increase in pressure here as it's going through the valve. The valve is still very closed, so there's still a very high pressure loss, but as the valve opens more and more, we see lower and lower pressure loss through the valve. We also see that pressure wave or that pressure front start to develop. So it's creating that high to low pressure. Again, if we remember that initial steady state case, we expect a smooth decrease in pressure, and then it'll actually more linear decrease in pressure, and it should drop off more dramatically towards the end as it starts to sonically choke. So we don't have to go time step by time step. If we click play, we can see how that pressure is evolving. So here we're at 1 second, so our valve is no longer the limiting factor, and our pressure wave is close to reaching the end of our system, where again, we're getting more and more pressure built into the system. And here you can see it's starting to sonically choke. You see that higher velocity, that higher pressure loss as it goes through the end of the piping. And it continues until we should see something approximating our steady state value. So if our question was, hey, when do we achieve a steady state pressure profile or something close to steady state, it would be about 4 seconds. If we speed this up, again, we ran this transient event for 120 seconds because we're modeling the full blowdown of the tank. And let's actually jump ahead quite a bit. So here we can see how that tank pressure continues to decrease as we're discharging the tank, continues down further and further. We're still sonically choking. And as we get further and further, that steepening of the pressure loss at the end gets less and less dramatic as, again, we continue discharging the tank. So that's the pressure. Before we look at some of the other parameters, let's take a look at the tank pressure directly. So now, instead of looking at how parameters are changing with the length of the pipe, we're purely looking at what are the conditions of the tank, our pressure and our temperature, and how do those decay over time. So we see we start at that initial 45 bar, and we see that exponential decay. We have the highest flow rate here, the most mass coming out of the tank. And as we lose our driving force, we get lower and lower flow rates and driving force. So if our question, let's say we're doing a theoretical analysis, and we want to know at what time do we hit 10 bar of pressure, we can bring it down to here, and we see it's about 175.5 seconds. Similarly, as we're discharging the tank, not only is the pressure decreasing, we can also see how that temperature is decreasing as well. So a lot of times we recommend leaning on these graphs because it's a lot of information to try to interpret, showing not only how things change over time, but also how do things develop along the length of the pipe? How are things traveling through the system? Again, that's where you're getting most of the insight of your analysis. So you could similarly look at valves. You could look at some additional parameters, things like your tank volume, if that's changing, how much mass is in the tank, you'd see similar decay. Again, in a lot of cases, we should have the parameters that you're interested in. And we'll go back to this animated profile, and now let's add another layer of reporting. So now we'll look at both the pressure and the temperature in our system. And again, we're going to be animating. So we have our tank here on the left. Let me close this off. We have our valve, and then we have our discharge. And when we play our animation, here, originally we were looking at how that pressure was developing and how it was transmitting through the system. But we didn't really see that formal of a pressure wave. It's kind of implied here at this kind of inflection point, this more dramatic where it starts sloping up. Here, if we're looking at temperature, it's much more dramatic. So as we suddenly compress all of the static fluid, or the stagnant fluid, I should say, in the second pipe, part of that goes to increasing the temperature of the fluid itself. So we see that increase in temperature. Further, now we have that high pressure, we have more mass that we're going to compress, and we see that temperature increase and increase further. So much so, it's going from here about 146 degrees Celsius, here all the way up to 600 degrees Celsius. And if you remember in our output, I think it peaks around 910. So again, as this pressure wave is transmitting through the system, it's compressing all of the stagnant fluid, increases the temperature, and again, we see that pressure profile start to develop over time. And we see it continues to increase in temperature. Excuse me, it's a bit squirrely. So let's set it to 6 seconds. And we can see how it reaches the end of the pipe and becomes less dramatic as it essentially vents all of that hot nitrogen, in this case, out to atmosphere. So here we can see again, transmitting through the system, it's transmitted through. We see that new steady state operation. And again, the tank gradually empties and our temperature of the tank also decreases. If we look at velocity, so again, adding another layer. And here, if we start our animation, we similarly see that velocity wave. So high velocity, again, compressing all of the stagnant fluid. And we see how that transmits through the system as well. And it starts to essentially flatten out. It doesn't maintain its steepness throughout. Also because I believe you'll see kind of some pressure wave traveling backwards as it hits it, things like kind of small reflections. And again, it can be a lot more challenging performing compressible transient analysis because you have all these thermodynamic effects as well. It's not just pressure and velocity like we see with liquid flow. Now we have sonic choking at the end of the pipe, for example. We have temperature that can be changing, density that's constantly changing. If you're modeling heat transfer effects, all of those things have to be in consideration for your result. And again, we see velocity fully developing, that temperature traveling throughout the pipe, and now it is discharging to atmosphere. And we see that sudden drop off of temperature at the end, I believe due to that sonic choking condition. And finally, we can add density. And so we will skim through here, and we see it starts at very high density, where it's very high pressure, and then it becomes lower and lower density as it transmits through the system. And again, it should achieve that steady state operating point, that steady state profile we would look for, and then gradually decrease the tank pressure over time. Obviously, this is a very simple system, but you can apply it to more complex things, like we were looking at that turbine system in the assumptions and applications. And then it'll model, not only how is the tank changing, how are you going to create pressure waves, how is that going to transmit and reflect and interact with other components in your system. Sweet. So the last thing we'll show one more workspace layer. We'll look at the color map, and then we'll compare adding heat transfer, how does that impact our results? And then we'll talk a bit more theory about pipe forces, and then a bit more theory about how the backend solver works. So the majority of the software use will be in the front half of the webinar, and then the back half will be kind of contextualizing the results and what we've explored so far. So we'll add a new layer for a color map animation. And here, let's animate the pressure. So if we go into the color map, here we can create a strict color map, which will color it based on steady state results. So let's say we look at our velocity at the outlet. So here we can see it's not a very interesting color map. It's 0 meters in, 0 meters out, or for pipe 1 and for pipe 2. If we look at our pressure instead, let's see, I have to run through the alphabet in my head. So the inlet pressure, we're at 45 bar, which we color red, higher than 37 bar that we've specified. And then here we have essentially no color. It hasn't met that 1 bar criteria at the bottom. We can also animate our color map though, and now we're tracking how are our parameters transmitting through time. So instead of the profile graph we were looking at, where it's changing with the y-axis, now we're changing it with color. So we have very low pressure to begin with, very high pressure on this side. And if we change this to our bar units, again, it's more consistent with what results we were looking at. So we'll close this out. And as before, we can step through our results where our valve opens. We see that pressure profiles start to get created. Here it's running very quickly. Let's slow it down. Let's restart it. So we have our high pressure and our low pressure. We open up the valve. We start to see that pressure profile generate. This also demonstrates why it is usually good to space your system out as it is in the physical system. Because this pipe is so much longer, these minimal sections, they should be very similar across each of them. So this length should be the same as this tiny length, and that's why it looks like this travels so slowly, when in reality this is, you know, almost 5 times or much larger than it should be in the actual system. But we can similarly show how pressure changes, how temperature changes. If you have wave interaction, it might be hard to show in a profile graph, but it might be easy to show in a color map animation. The last thing we'll talk about is transient forces, which I don't have in this example, but you can also specify a transient force, for example, maybe at this valve, or a point force, or if you're looking at elbow pairs, how do you have an axial force that acts on it? And again, those forces can be exported into Caesar if you're looking at pipe stress analysis. I was talking with an engineer recently. They were looking at a case where they had a T working on a turbine system, and they were seeing failures at that T. And so they were looking to AFT xStream to model those pipe forces, see if that could trigger a fracture or a failure at that component. So quite a few ways to review your output. Again, output, more tabulated information, but that can be challenging as you have more and more data with transient output. Graphing, which is what I would recommend, either graphing how parameters change over time, like we saw in the tank, or seeing how different parameters are changing with one another along the length of the pipe, animating it through time. And then finally, the visual report, where you can add, you know, individual reporting metrics for steady state analysis, or what's your maximum transient analysis. And then also color coding your system either at steady state or seeing how parameters change along the length of the pipe as well as through time. So that's really the software introduction to AFT xStream. The remainder will be primarily theory, and then we'll talk about some additional capabilities and some resources at the end of the webinar. So the first thing is considering transient force calculations, where we have unbalanced forces. Again, this is more common in transient flow because you have those pressure waves and those changes in flow that's transmitting through the system. So depending on how those pressures and mass flow rates change, you're going to get different forces acting on your components. So it's important to account for pressure, changes in momentum, and frictional forces. So both changes in what's the pressure at this point, and also how much mass is going into and out of our control volume where we're calculating the force. Also considering frictional forces, so as your flow decreases, you're going to lose that frictional force, obviously pulling in a different direction. So we consider the pressure and the momentum on both sides. We do a summation of the forces, and then you can export those unbalanced forces to, again, a stress analysis software like Caesar2, AutoPipe, Vor2, Triflex, K-Pipe. Again, your kind of run-of-the-mill spectrum or time history analysis software. So if we take a look at an example, so here we have a system of 2 tanks, and we want to look at the difference force, or how much axial force is going to act on this leg of it. We see it starts at 0 at steady state. We see that peak force here of 40,000 newtons, and then it returns to about 0 force as the system then restabilizes. And again, all those forces can be exported, so that way you can perform that pipe stress analysis as a response to your transient hydraulic forces. All right, let's take a look at our summary. So as we saw, like all of our other applications, models are made up of pipes and junctions where the specification is pretty intuitive. We didn't talk about some of the components that can react to your changing system conditions, things like relief valves, or if you're triggering events, if you're triggering a valve to open if turbine conditions aren't met, for example. Again, transient analysis creates a lot of output. As we saw, as we're tracking all of the data along the length of pipes as well as through time. So it's best to graph it, animate it, use a color map, graph it, animate it, color it, pop it. I shouldn't let that in. Here, it's critical to understand how all the parameters interact. So as your pressures are changing, your velocities are changing, your temperature is changing. So all of those things go into your compressible transient solution. And again, it can lead to kind of less than expected results. So actually, before we go on, last thing I wanted to show in the software, which reminds me, is this convective heat transfer. So now we have a child scenario where the only thing that we've changed is adding convection to our pipes. So they're no longer adiabatic. They now have convective heat transfer, where we are also modeling convection or conduction through the pipe wall, and we have ambient air at 21.1 degrees Celsius. So the main question you should have is, well, what are the effects of heat transfer? Because our software can model heat transfer, how do you avoid those simplifications of adiabatic or isothermal, things of that nature? Because we've increased the complexity of our system, our runtime is also increased. For reference, it's increased to a little over 4 minutes. And again, as we'll talk about, it's important to create a staged approach, performing maybe an adiabatic analysis, then adding heat transfer, then adding more sections, things of that nature. And if we go to our graph results, we'll look at our same animated profile. Here, let's isolate the pressure and temperature. And I'm going to create a multi-scenario graph using this multi-scenario button, and we'll compare our base scenario without heat transfer, and then we'll compare it with our convective heat transfer case. So let's slow this down some. And so when we start our transient, again, we see both have that pressure wave. And here we see that with heat transfer, our pressure wave isn't as dramatic. It stays much lower. It seems to take a bit longer to develop. And if we look at the temperature change, here we see a very stark difference. The main thing we can contribute this to is convective heat transfer is going to also model, we call it thermal capacitance. I'm not sure if that's the technical term, but in essence, the pipe is fixed at a temperature because it's been exposed to near 0 degree nitrogen for however long it's been sitting in that pipe. So the piping itself is naturally at that temperature as well. So when you send a hot pressure wave, that thermal capacitance takes in some of that heat, it dissipates some of that compression heat, and so you don't see that same dramatic increase when you're looking at the pure fluid. And so if you play this out, here you can see the adiabatic case, you get a much more dramatic temperature rise. So that could be concerning if you were looking at, do I exceed a design temperature in my transient event? Hey, if you consider heat transfer, maybe it's not so dramatic. And also you can see how that temperature gradually decreases through the pipe, again, as the pipe is gradually heated throughout the transient event. We don't see that same temperature profile where it'll start hot and then I believe gradually cool due to adiabatic cooling as it depressurizes. Instead, it drops off pretty immediately and maintains that lower temperature. So simply by adding heat transfer, again, the conclusions of our analysis, depending on where you're looking and what you're examining, can change dramatically. And that's why it's important to invest in making more accurate, more realistic models to capture those effects at generally the exchange or the cost of an increased runtime. So here, if we jump ahead, we can see it gets closer and closer to agreement. And here we see kind of thermal retention going the other way. It's actually maintaining a higher temperature. And as it goes down, again, it's still fixed. But if we look at our tank pressure, let's do a multi-scenario graph of this as well. So now looking at what's our pressure in the tank. Here we see the pressure in the tank is very similar. If we were looking at our 10 bar condition, again, it looks like it's within a second or 5 of itself. So good enough for us. Again, maybe those temperature effects, if we're looking at max temperature, maybe that's dramatic. If we're solely looking at what is the heat transfer or the pressure depressurization of the tank, got there in the end, maybe adding those heat transfer effects are not as important. Hard part is we don't know until we try. So as we saw, the complexity of xStream Solver requires longer runtimes. It's a bit harder to do kind of quick iterations you might be more comfortable with in Fathom or Arrow or in Impulse. So be sure to structure your models with this in mind, setting up all your design cases, running them in a batch, leaning into the scenario manager. Then finally, the backend solver must consider the complexities of compressible flow, transient flow, and compressible transient flow, which will be the next segment of our presentation. So the first complexity we're going to tackle is the fluid is compressible. As we saw, we have to recalculate fluid properties as pressure and temperature changes, density changes, all of those things are interacting with one another. And then also heat transfer can have more dramatic effects. So if you're heating up a gas, it's going to expand, whereas if you heat up a liquid, the density doesn't change as dramatically. Maybe its viscosity might change. So what's important to realize is isothermal and adiabatic may not be reasonable. It might be the difference between a peak temperature of 900 in your system versus a peak temperature of, I think it was 25 or 15, something of that nature. So to highlight this compressibility, sort of like what we saw already, all of these parameters are interacting with one another. So as your flow rate develops, it impacts your pressure drop through the system. That impacts your density, which the density informs your velocity, your flow rate, which informs your pressure drop. Again, all of these things are interacting. And then also those heat transfer effects, temperature, things of that nature. So here, a little bit of a different system, an inlet tank, a discharge tank, and an orifice in the middle. But we see that similar kind of linear pressure drop until it starts to fall off dramatically. Kind of linear increase in velocity until it starts to increase as it starts sonic choking. Similarly, linear decrease in temperature and then dramatic off as it increases in velocity. So we capture this using March methods. So we split the pipe here and we can split it based on length. Let's say we split it into 10 even sections, or as it gets faster and faster, we split it based on change in velocity. So as it accelerates, if you remember when we were looking at our graph, you get more and more points as it gets faster and faster because we're recalculating those fluid properties to capture that sonic choking effect. Next is we need to evenly space our sectioning to use the method of characteristics, a lot of words that we'll make a bit more clear here in a moment. So like in Waterhammer analysis, signals take time to travel through the system. If we slam a valve closed and we're looking at a Waterhammer event, that pressure wave doesn't immediately arrive upstream. It has to travel. Another analogy is if you clap your hands, it takes time to travel through the medium, through the air, at the acoustic velocity. And similarly, you're going to see that with pressure waves in both liquid and compressible flow. So the way that we can capture how long it takes those things to transmit is using what's called the method of characteristics. The most simple way of explaining it is we divide our pipe into these discrete sections, and we can see how these different sections influence one another as we travel through time along this y-axis. So let's say we have a pressure wave that starts here. This point in our pipe won't see that pressure wave until some time passes, and we can evenly space this so that way our calculation points, they always line up on this grid nice and neatly. What does this look like practically in the software? Here's an example from AFT Impulse where we're looking at a valve closure. When we create a signal, in this case a high pressure wave, we see that it transmits through the system. So each of these lines you can think of as a point on this grid, and as we track them through time, we see, hey, there's a high pressure. We can expect that high pressure to transmit to the next adjacent point in that next time step. And again, it transmits, it reflects, it travels through, accounting for pressure, for your velocity, for your temperature, all the things of that nature. So we have effectively two types of sectioning now. We have the AFT arrow sectioning, and now we have the AFT impulse sectioning, considering compressibility effects and considering tracking our transient transmission. The third point with compressible transients is the magnitude of the bulk velocity. This is how fast the fluid is moving through the pipe, and the wave speed. The wave speed is essentially how fast this pressure wave transmits through our piping. Let me see. So we can see it's moving relatively quickly. This isn't based on the flow rate of the system in liquid flow. For example, in a steel pipe in water, the wave speed might be 4,000 meters per second. Similar, if you hit iron, sound and pressure waves transmit very quickly through a solid, much faster than through a liquid, and liquids much faster than through gases. So with compressible transient flow, not only are we considering this wave speed aspect, how quickly the pressure is transmitting through the system, we're also considering this bulk velocity because they're now on the same order of magnitude. That means when we look at our method of characteristics grid, when we're dividing it up to track how things are changing over time and through distance, we're also considering that bulk velocity. This also means the solution will be more sensitive to sectioning, especially at those higher velocities because of how we've created the grid and how we have to perform these calculations. So let's look at our modified MOC. Again, we're looking at both the bulk velocity and the wave speed. For liquids, it's easy. The wave speed is much, much faster than any liquid should be flowing. So we get these nice, neat points, each of these sections on our pipe. And along one time step, we can calculate here's what our new pressure or velocity or etc. will be. So it's informed by those adjacent points. And then as you progress through time, you continue performing that calculation. However, with gas and steam, because we're also considering the velocity, the points that we're referencing may not fall neatly on our grid. So what we have to do instead is some calculation for interpolation to again determine what is our property, what is our result at this point. That gives us then a new grid. We run our calculation, we look back, and we can perform that same interpolation. Here, we're looking at the wave speed. Here we have to essentially make our grid a bit larger based on this Cmax, and that is our maximum wave speed, essentially, which is going to be based on temperature, which we'll talk about here in user input. So as we're specifying a model in xStream, we have a few more things we have to specify. We have to include the minimum number of sections. So how are we splitting that pipe up? And it's also important, users should perform sensitivity so that we can confirm our result accuracy. So usually pipe sectioning is done for you in AFT Impulse. We say, hey, this is an acceptable error. We're going to do it for you, and then we'll go ahead and run your model. In xStream, we're putting a lot more trust in the user to add the number of sections. And so as you improve your model, improve your analysis, you can increase this number of sections until you get a consistent result. We also require an estimated maximum pipe fluid temperature. Now you might be asking, well, I don't know that temperature until I run the model, and that's where you can perform those iterations. You can provide an estimate, maybe a much larger than you would expect estimate so that it runs without issue, and then gradually bring that down as you have subsequent runs and you're getting more and more accurate. So this fluid temperature, again, faster fluids, typically waves travel faster through them. So that informs the Cmax calculation. That's really what's informing this horizontal spread. Both of these factors, both the minimum number of sections, maybe it's 2, maybe it's 10, maybe it's 100, depending on your system, and this maximum temperature, which again informs this velocity component. Both of them section the grid, determining both the distancing and then also the time that it takes to transmit through the system. When we initialize our solver, if we remember, we initialize from AFT arrow, which in sonic choking cases might have sectioning that looks like this, kind of very fine resolution towards the end, capturing all of those property changes. And we have to transmit it into AFT xStream, which has this very structured, very evenly spaced grid. So the way that we do that is we put in our AFT arrow results. If there are any differences, we run our transient solver until those artificial transients being things that aren't realistic in the system. They're solely caused numerically due to differences in how the solution was structured. Until it resolves out, it finds a new steady state, and then we perform our transient simulation. Again, this mismatch, depending on how you section the model, obviously the more sections you add in xStream, the finer resolution you can put your arrow results into, the less artificial transients that you'll see and the lower mismatch you'll see in your final results. That's what we mean when we say that the number of sections in xStream are going to be more influential than in something like AFT impulse. So finally, some implications on analysis. We want to look at bulk velocity and wave speed. We can model real gases, also considering heat transfer effects, capturing those compressibility effects. And we do so by trying to minimize the limiting assumptions. Pressure waves can also coalesce or disperse over time, so that wave speed aspect of it can also change with temperature, so it's not as fixed as you might see in AFT impulse. So in summary, compressible fluids, again, pressure, temperature, velocity, pressure drop, all of those things are interrelated, and so we have to perform calculations to recalculate those fluid properties. Your pipe sectioning is going to capture your changing pressure, temperature, velocity, density, all along the length of the pipe. So we have each of those reporting stations, and it's important to have sectioning small enough to make sure you're getting accurate results, but the more sections you add, it's going to add additional runtime. Finally, we use AFT arrow results to initialize the solver so that we can get rid of any artificial transients before the transient xStream run. So we'll touch on some modeling recommendations, and apologies, I believe we'll go over the hour, but hopefully not by more than 10 or 15 minutes. And if you're watching the recording, spoiler alert, you know how long the video is, and then I don't. So some modeling recommendations, we will start simple and then get more complex. So because runtime can be more dramatic, look at how you can simplify your model as much as possible. So that way you can get those quick iterations. You can see what's kind of the bulk response of your system, and then get it finer and finer resolution for things like pipe stress, or what are your final pressures, what's your final delivery time, things of that nature. As you get closer, you want to increase your number of sections, so that way you're getting more and more accurate results. You're removing any kind of error introduced by sectioning. However, again, as we mentioned, the more sections that you add, you're going to increase your calculations. So how many points and how many time steps are you calculating? And therefore the runtime to perform all those calculations, and that increases exponentially. So if you double your number of sections, it doesn't double your runtime, it will actually quadruple it. And again, lean into how you're building your model, so that way, if it does take that long, you can run all of your cases, come back, do your analysis. Maybe you run your systems overnight, things like that. All right, we'll touch briefly on the add-on module, the pulsation frequency analysis module. This is for acoustical natural frequencies and determining where reciprocating compressors avoid resonance with those frequencies. So a lot of compressors are PD compressors. That causes a lot of oscillation, and that can lead to vibration and other concerns. So the PFA module determines your acoustical frequency, says, hey, you're activating or you're resonating at this frequency. You want to avoid operating your pump or other equipment, or compressor, I should say, where it's going to resonate with this frequency. And again, you can also test the frequency for your peak-to-peak pressure, what's acceptable against the API standard 618. So how does it work? We have a system where we want to examine our acoustical resonance. We ring the system using a forcing function. So this tests a range of different frequencies, or it's essentially a high energy pulse, I should say. And we can look at the response and say, hey, we have some different high points where we're resonating. These are the frequencies of the system. From those frequencies, we can get a function that'll inform essentially the compressor and how quickly it will operate, or something that'll activate that frequency. And that gives us a worst case scenario, what's our peak-to-peak pressure at that point. And again, it considers the API 618 standard, where it'll indicate to you whether or not the peak-to-peak pressure is exceeded. And you can further use the module to size dampening equipment, identify speeds to avoid. And the main concern, especially with pulsation, is the time to failure can be very short because you're constantly inputting energy. Again, think of the swing. If you're perfectly timing your push, you're compounding all that energy, and that leads to a very short time to failure. All right, to wrap up the webinar, obviously it's a lot of information to try to take in. So if you're looking for more things to learn about AFT xStream, this is where I would start. The quick start videos or the guides, it'll go through a more structured introduction covering things like model input, fluid properties, defining your sectioning, making graphs, things of that nature, things I kind of take for granted in this introductory webinar. If you like webinars, which I imagine you do if you made it to the end of this one, we have a lot of different webinars on a lot of different topics, whether that be liquid flow or transient Waterhammer analysis, xStream, compressible flow. Again, all of those are captured in hour-long lectures. Our documentation, which is all available on our website at docs.aft.com, goes into a lot more detail on equations, provides examples. What we looked at today was an example file, and also goes into more detail about what specific parameters mean as you're doing model specification. Some additional resources, you can learn about training seminars, tips and tricks blogs, technical papers, articles, case studies, etc. You can find all of those on our website at aft.com. And finally, some consulting resources with the complexity of xStream. Typically, if you're buying a lease or a perpetual license, you can use engineering support based either in the US or regionally local to your country. And again, we have decent experience working with xStream, getting to massage it, getting the results that we need. And again, it's valuable having an expert because engineering projects don't exist without a deadline. Someone's always pushing it forward. For a more complex analysis, you can purchase a Flow Expert package, either 5, 10, or 20 hours working with an AFT engineer to review your model, your results, and teach you your fundamental modeling concepts. And then finally, with Purple Mountain, we also do a consulting, or this is our consulting sister company. So if you have a transient compressible event that we want to examine, but you don't feel comfortable performing the analysis directly, you can contract that work out. We'll issue a proposal, we'll build a model for you, we'll write a report. You can then pass that along to your final client, or you may be the final client. So in summary, as we saw, if you have experience, all of those things are going to translate to xStream. So global edit, all of your scenarios, your graphing knowledge, all of that translates to AFT xStream. And if you don't have those skills, there are plenty of webinars to help you get there. While AFT xStream makes all of these compressible transients accessible, again, it's pretty simple to build a model. It's very important to understand not only the underlying hydraulics and thermodynamics, it's critical to understand how does the solver work and how can that impact your results. Even more so because it's going to be more calculation intensive, again, recalculating fluid properties depending on how we're sectioning the model, doing those interpolation calculations. It's important to take a strategic approach to work efficiently. So start with a simple model and then increase your complexity. Maybe you add more fluid specifications, you add heat transfer, you add additional sections. And then also, of course, ensuring that you have enough sections for an accurate model, an accurate representation of the physical system. A lot of content, especially if you've made it to the end. I'd like to thank you and congratulate you for attending. If you have any other questions that we couldn't address during the webinar, please email them to webinars@aft.com and we'll do our best to respond to them. If you have any ideas for future webinars, you can submit a topic to webinars@aft.com. We're always curious to hear what users are using our software on and how we can use these webinars to further educate other users or engineers on hydraulics in general. Again, my name is Nick Vastine, Business Applications Engineer with Applied Flow Technology, and we look forward to having you in another Applied Flow Technology webinar soon enough. Thank you.